Thank you, Lars. Thank you, Franz. My name is Colin Campbell, and I have the real privilege of leading powertrain engineering here at Tesla. We make the fastest cars that you can buy for the money, whether they're electric or gas. And the Model S Plaid that we're looking at here, it has more than 1,000 horsepower, and pound per pound, the motors in that car are as powerful as jet engines. Our cars are super fun. People absolutely love driving in them. And the other thing that you probably all know about our powertrains is that they're efficient. Our cars go 25 to 30% further than other EVs in our class for the same amount of efficiency. But at Tesla, efficiency means more than just reducing how much energy the cars use. It's about how we develop, how we manufacture, how we refine, and how we scale the powertrain. Now, the Model 3 and Y powertrain is a great example of this broader meaning of efficiency. So since we launched it back in 2017, we've continuously improved that powertrain and the factory that builds it. So the drive unit, the engine of the car, is 20% lighter for the same power. We use 25% less heavy rare earths than when we started. And the powertrain factory, which is behind me today, is 75% smaller and 65% cheaper than the one that we originally built. And what I really want to emphasize is that we did all of this without compromise. Our cars are just as powerful, they go just as far, they cost the same or less, and the factories have the same output. So, how did we do that? We did it by designing the entire vehicle and the entire factory together as one company. And this sets Tesla apart. We have small and highly capable teams, and to make a critical decision, we can have the battery cell chemists, the mechanical engineers, the manufacturing engineers, the supply chain team, the automation designers, the software programmers, all in one room, working together in real time. And that allows us to make decisions that are best for the whole car and to make them really fast. And that approach is unlike traditional automotive engineering, which is really fractured. And if you were to go buy like a premium German electric car, the engineers who designed the drive inverter in that car, they did not work for that car company. They worked for a contractor. And at Tesla, we designed the entire car and the factory that builds it. And I want to highlight a few examples of what we've been able to do in-house thanks to that unique approach. So, inside the charger of your Tesla are transistor packages, and that's at the top of your screen here. And every electron that moves you down the road flows through one of these packages. We designed our own custom package, which is what you're seeing here, and we can extract twice as much heat out of that package as what we could buy off the shelf. And so what does that mean? It means that the silicon carbide wafer that's inside those packages can be much smaller. And silicon carbide is an amazing semiconductor, but it's also expensive and it's really hard to scale. So using less of it is a big win for us. And then on top of that, orchestrating all of these transistors and making them switch in the right ways is computationally extremely intensive. It used to require 4 microprocessors, which are shown here in the bottom left. We have developed our own custom microprocessor. It's purpose-built for high-power electronics. It's half the cost, and it does, in just one, the job of all of those 4. And these are just 2 examples of many that I could use to showcase our expertise in high-power electronics. And that expertise has allowed us to take the cost of the chargers that were in our Model S when we launched it in 2012, both the cost and the mass, and cut both of those in half. And even more important, power electronics, they're central not just to our cars. They're also central to our superchargers and to our energy storage products, and Rebecca and Mike will be talking more about that. So in addition to the work that we've done in software and hardware, we've also done a lot of work in-house on software. So this is the drive unit for Model 3 and Y, and if we take a cross-section, we see the stator and the rotor, and they're responsible for the core function of the drive unit, which is converting electricity into motion. And our custom software lets us simulate the rotating magnetic field that is responsible for that conversion. And getting that simulation exactly right, it's central to the cost, the weight, the size, and even the sound of the drive unit. And now, you can buy software that will do all of this, but our tools are faster, and they're more accurate, and that was not easy to do. And that allows us to quickly iterate through millions of possible drive unit designs to find the best one. I want to highlight one more area where Tesla really excels because we integrate work that is often farmed out. So when you are making a new product, it's not enough to think about the product itself. You have to think about how you're going to make it at scale. So at Tesla, our powertrain and our powertrain manufacturing equipment is both designed under one roof. The engineers who are designing the motor, they are in the same room as the engineers who are designing the machine that's going to put that motor together. And that collaboration pushes us from day one to design products that are not only high performance, but are really easy to assemble. So, all of this expertise that we have in the powertrain team, in hardware, in software, in manufacturing, it's going to have a major impact on our next platform. In our next powertrain, so those silicon carbide transistors that I mentioned that are key component but expensive, we figured out a way to use 75% less without compromising the performance or the efficiency of the car. And of course, we know that battery cell supply is one of the constraints on the scalability of EVs right now. Our new powertrain is compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000. And we don't think any other automaker is even close to that number. Finally, the bigger a factory is, the longer it takes to build. If we can build the same number of cars from a smaller factory, we are going to be able to scale EV production faster. Our next powertrain factory is 50% smaller than the one that's behind me today, even though it has the same capacity. All of these improvements, I think, are going to be transformative for the adoption of EVs and our ability to scale them. There's one more thing that I want to highlight. So I talked about how we had reduced the amount of rare earth in our powertrains. And as the world transitions to clean energy, the demand for rare earth is really increasing dramatically. And not only is it going to be a little hard to meet that demand, but mining that rare earth, it has environmental and health risks. So we want to do even better than this. We have designed our next drive unit, which uses a permanent magnet motor, to not use any rare earth materials at all. So how does all this fit into the master plan? We can make lower cost products that are still efficient and compelling, and we can make them at scale. We're going to use less of constrained commodities, silicon carbide, rare earths. We're going to build them all in compact and high output factories that are easy for us to build quickly. We're going to make that easy to scale powertrains all the way up to the levels that Drew and Elon mentioned at the beginning. And this achievement, like all of the achievements that I mentioned today, it's only possible because of the incredible people on our powertrain teams. They are absolutely committed to the cause of sustainable energy, and that is why we can do what no other company can do. Thank you.